When an industrial machine faults, the real danger is what you cannot see. A controller running blind can trigger catastrophic mechanical failures before you even realize a problem exists. Today, we are taking control of a Siemens S7-1200 PLC to recover it from an unknown error state. We will extract the system alarms, synchronize the internal clock, and execute a complete factory reset. Executing these specific maintenance steps replaces guesswork with hard data. You gain absolute, verified certainty about your controller's health. Step 1 is establishing the physical link. Ensure your PLC is powered on, connected to your computer via Ethernet, and loaded into the TIA Portal software. Navigate to the project tree interface on the left side of your screen. If you have multiple devices listed, select the specific target named PLC_1. Here is the most common point of failure. You must activate the Go Online mode before you can read any data from the device. Check the Properties tab at the bottom of your screen. Look for the green indicator to confirm your active online connection status. This critical digital handshake establishes our baseline. Without an active connection, any diagnostic data you see is a static, outdated snapshot rather than a live feed of the machine's processor. With the connection live, select the Online and Diagnostics menu to access the core troubleshooting interface. This wireframe illustrates the Diagnostic Buffer. This specific menu serves as the central hub for logging all alarms and system events. Look closely at the event list for critical state changes. You can see exactly when the CPU shifts abruptly from start to stop mode. The buffer operates as the system's flight recorder. It takes ambiguous machine failures and logs them chronologically to tell the exact story of a crash. Next, direct your focus to the Network Settings pane to verify the identity parameters of our controller. Check the MAC address, the assigned IP address, and the subnet mask fields. You must confirm these details match your network documentation to ensure you are communicating with the correct node. Moving to the Set Time function, we apply the current PC time directly to the module to synchronize the internal clock. If you skip this step, an unsynced clock records inaccurate timestamps. This renders the diagnostic buffer completely useless for tracing the sequence of a root cause. Accurate time synchronization provides the necessary context. It organizes a random list of errors into a precise, actionable timeline. Still within the Diagnostics menu, you will find the command to reset to factory settings. Executing this command permanently wipes the current configuration. Use this only when you need to clear all previous data and start with a clean slate. This schematic details the S7-1200 hardware chassis. We must match our software settings to the specific physical constraints of this compact model. Notice the restriction on the right side. Because this is a secure, compact version, you cannot attach standard I/O modules here. However, looking at the left side, the architecture safely allows the addition of up to 2 communication modules. Knowing these physical constraints prevents hardware damage. It ensures your system architecture is physically viable before a single line of programming logic is written. We have moved the controller from an unknown, potentially faulted state to a fully diagnosed and clock-synced system. By utilizing the software's reset capabilities and respecting the hardware's physical expansion limits, you ensure the device is ready for reliable deployment. For deeper automation courses and detailed programming guides, check the links in the description below, and be sure to subscribe to the channel. Your controller is now cleared of legacy errors and structurally secure, ready to process a clean, optimized stream of programming data.